Thank you very much. So it's a great pleasure to be back here at Lumini. I'm very thankful to the organisers for inviting me to speak. And yeah, I apologise. I'm going to talk about a slightly broader topic than what my original title in abstract was, but it's going to be closely related, so it's not going to be too different. So I want to talk about primes and thin sets. And the basic question I'd like to think about is you give me your favourite set of integers A, so given some set A in the natural numbers, and I want to think about thin sets. So let's say that the number of elements in A which are most x is bounded above by x to the power 0.99 for concreteness. So you choose your favourite thin set A, and this is what I mean by thin. And I want to know how many primes are in A. So obviously in this level of generality, this is a hopelessly broad question and touches on many famous open conjectures. So just to name one for concreteness, one of these 100-year-old open problems is, are there infinitely many primes of the form n squared plus 1? And this is something that's way beyond anything we can hope to prove, but certainly would be a very nice result. If you're someone who prefers to think about cancellation of Möbius rather than counting primes, the alternative question that you might prefer to think about is some sort of Möbius randomness cancellation when I'm restricting to some set A of interest. So is it the case that if we sum the Möbius function for n less than or equal to x and n in A, well, since A contains only x to the 0.99 numbers less than or equal to x, this is certainly going to be little o of x, but is it little o of the number of elements of A which are less than or equal to x? And in various non-rigorous but moral senses, these two questions are very closely related and often very similar. So I guess my talk's very much more on the arithmetic and combinatorial side of things than so much on the ergodic side of things. But hopefully what I'm talking about will be of interest to at least a majority of people in the audience here. But the fact that I'm dealing with thin sets here really causes lots of analytic difficulties, and in particular almost necessitates the fact that we need to use lots of hard analysis rather than soft analysis that often comes out as a product of ergodic theory. So to relate it to something that some members of the audience might be more familiar with, if you have a fairly dense set here, then you might try and prove cancellation of the Möbius function by using a version of the Cat-High orthogonality criterion, as Bourgain, Sarnak, Ziegler do for horocycle flows. But the Cat-High criterion can't apply to thin sets. Roughly, you do a Cauchy-Schwarz once, but the diagonal terms will dominate. And so you can't use the the sort of soft version of orthogonality criterions that come out from the type arguments, and you need to use hard bilinear estimates rather than the soft type bilinear estimates. So Katai orthogonality criterion doesn't apply. It sort of necessitates hard analytic estimates, and even maybe the simplest cases, it actually requires some quite deep results on the distribution of prime numbers. So maybe the simplest possible set you could think of this type would be just short intervals. But to prove that there's always a prime in an interval around x of size x to the power 0.99 already requires an improved zero-free region and a zero density estimate. So this is Hoheisel's result, and is already using quite a lot of machinery we have connected to the Riemann zeta function, and in particular goes a lot further than just the Riemann hypothesis. So even simple cases of short intervals and similarly arithmetic progressions require deep estimates for L functions so things like zero density estimates, improved zero-free regions, in the case of arithmetic regressions, this would be using some sort of Doering-Harbon zero repulsion phenomenon. And you have issues with Siegel zeros. So even in maybe the easiest possible cases that you'd hope to try and answer a question like this, we can get some answer, but it really requires quite deep techniques from the theory of L functions and the distribution of zeros of the Riemann zeta function and Dirichlet L functions. So maybe given this, if you're looking for examples which aren't essentially short intervals or arithmetic progressions causing sparsity, and that's really what I'm interested in today. I'm not interested in things that are directly to do with distribution of zeros of L functions. I'm trying to think about sets A which aren't just some linear set where we've made some restriction. It's probably not too surprising that there's a very sparse set of examples, and there's only a handful of cases when we can actually say anything whatsoever. Just take this all the way up. Outside of arithmetic progressions or short intervals, or things that somehow look like arithmetic progressions and short intervals hidden slightly, there are very few examples. Cases when we can say anything at all, but there are some. So there's the work of Friedlander and Ivanich saying that there's infinite many primes of the form x squared plus y to the 4. And a recent generalization of this due to Heath, Brown, and Lee, where you can take y to be a prime number. There's x cubed plus 2y cubed, which is due to Heath-Brown, and then there's a generalization of this due to Heath-Brown and Marotz for general binary cubic forms and some cubic polynomials. And then a final example that I'll give is that you can pre-specify a positive proportion of the binary digits of primes, and this is work of Bourgain, but uses various ideas based on work of Maury and Rivard. So here it's saying you can choose some very small but positive proportion of the digits. You fix those in advance, unless you're choosing a stupid digit like the final digit being equal to 0, then you have the flexibility. You can choose the remaining digits and force the number to be a prime number. And so I guess in terms of logarithmic density, originally I was asking for sets that have logarithmic density at most x to the power 0.99. This is a set that has logarithmic density x to the 3/4. This is a set that's sparse, logarithmic density x to the 2/3, and this is logarithmic density 1 minus epsilon for some unknown but very small constant epsilon. And what I'd like to talk about today is a few more examples of sparse sets of numbers, which are in fact going to be somewhat related to these examples, where we can count the number of primes and we can show that there's infinitely many primes. So the first result I'd like to talk about is given further examples of polynomials that take on infinitely many prime values, so multivariate polynomials. So these can be viewed as weak forms of the x squared plus 1 conjecture. So I'm not quite sure the best way to state it because the precise polynomials are slightly technical, so maybe I'll state it in a weak form. So for every pair the n of integers there exists an explicit polynomial f dn, which I'll just call f, of degree n, of degree d in n variables, such that if we want to count the number of primes less than or equal to x, such that p is a value of f, this is equal to, okay, I'll use this notation to denote asymptotically equal up to a multiplicative constant, so maybe out by a factor of 100 in both an upper bound and a lower bound, some constant depending on f times x to the n over d divided by log x. So I need to say something about n and d here for, let's say, d bigger than n, bigger than 15 over 22 d. So these are homogeneous polynomials, and they're taking on a sparse set of values here because n is less than d. So if you wanted to count values using, say, the Hardy-Littlewood circle method, typically you could count the number of prime values of a polynomial, but only when the number of variables is huge compared to the degree. So the number of variables would need to be exponential in the degree, whereas here, I'm not having the number of variables as being anything like exponential in the degree. It's actually less than the degree, so it's a very sparse set. So it's much more like the examples of Friedlander and Vanniech and Heath-Brown, and at least up to a multiplicative constant, I can get the right order of magnitude for the number of primes represented by such a polynomial. And I'll give one explicit example of the polynomial for a degree 4 polynomial and 3 variables. Somehow, morally, this example is the wrong example to give because this precise polynomial could actually be proved using a small generalization of the techniques of Heath-Brown here. However, the polynomials naturally get pretty difficult to write down, and so this is the shortest polynomial to write down. So it's a pretty poor example, but it's the only one that I'm going to have time to write down. So you could take the polynomial f of x, y, z to be x to the 4 minus 2 y to the 4 plus 8x y squared z minus 4x squared z squared plus 4 z to the 4. So in particular, I actually find an infinite family for any given d and n satisfying these conditions, but these aren't any old polynomials. These are very structured polynomials. And in particular, these are polynomials that are very closely related to norm forms. In the same way that it turns out the two polynomials of Friedlander and Vanniech and of Heath-Brown are both very closely related to norm forms. And this is very important because the extra structure buys you a bit of extra room for movement to come over some of the analytic difficulties of dealing with such a sparse set. So that's the first example of primes in thin sets that I'd like to mention. And then the second example is going to be a more combinatorial example where I want to look at the decimal digits of primes, and I want to count primes that have no 7s anywhere in their decimal expansion. And the same result can hold with 7 replaced by any other number. But for the sake of concreteness, let's talk about 7. So I want to look at the number of primes less than or equal to x, such that P has no digit 7 in its decimal expansion. Then, again, up to some multiplicative constant, well, the number of integers less than or equal to x with no 7 in their decimal expansion is roughly x to the power log 9 over log 10. And then maybe it'll be unsurprising that the density of the primes inside the integers will be a constant divided by the logarithm of x. So in particular, this means that there are infinitely many primes with no 7s anywhere in their decimal expansion, and similarly, you can replace 7 by 0 or 1 or 2 or whatever you like, and you get exactly the same result. You can do the same for any base which is bigger than or equal to 10, and when the basis gets large, it becomes much easier, and you can start excluding multiple digits, but the argument I have, at least, doesn't work for any base smaller than 10. But again, this is a sparse set. It has logarithmic density log 9 over log 10. I guess the sets of polynomials I was looking at here have logarithmic density slightly bigger than 15 over 22, if you're choosing n to be 15 over 22d. So these are both sparse sets, 15 over 22 is about 0.68, so it's slightly less sparse than the Heath-Brown example, but sparser than the Friedlander-Vanich example, and both of these are sparser than the Bourgain example. So the key point is I have two more examples, slightly isolated, of thin sets of integers that contain infinitely many primes. So as a remark, for those of you who are who prefer the Möbius randomness side of things, actually, it's a strange feature of these arguments that they don't give full cancellation of Möbius. The natural analog of these only gives that you get some small amount of cancellation, so you can show that there's something like a positive proportion of sign changes as you go along the size of your set A, but you get 1 minus c times the size of A as your bound for the sum of the Möbius function. However, if you weaken both of the questions that you're looking at slightly, then you can get full cancellation of Möbius. So if, say, you make n be at least 3/4 d, then you can get the same version of theorem 1 with little o cancellation of Möbius. And for here, if you replace decimal expansion by base b expansion, where b's are large enough constants, and I think sort of 20 or 25 might do, so maybe if you count with your toes as well as your fingers, then you'd be good enough, then you could get cancellation of Möbius. Okay, so those are the results that I'd like to talk about today. These are all totally consistent with the sort of heuristics that you might have to do with Möbius randomness, to do with the primes having density 1 over log x, but maybe you having some correction factor based on products of local densities and things. All of these fit exactly with all the heuristics that one might possibly have in general, but the key point is that there's significant technical difficulties when you're trying to deal with sparse sets. What should I leave up? Okay, so I'd like to say a little bit about some of the ideas of the proofs, but without getting into too many technical details. So I mentioned before that if you want to prove a case of Sarnak's conjecture, for example, then typically you might well use the Katai orthogonality criterion to reduce the problem of showing cancellation in Möbius to the problem of understanding a certain bilinear sum. And this is one example of an old principle of Vinogradov to do with estimating the Möbius functional primes by decomposing it as a sum of things that look like easily handled terms over arithmetic progressions, so-called type 1 sums, and then the so-called type 2 sums, which are bilinear sums. And so there is a variant of the bilinear sums which enable you to prove all of these results, and all of these proofs do work by using bilinear sums, but you need to do it in a slightly harder analysis way with uniformity in the size of the pairs of primes that maybe you're looking at. So I'll just write this in a slightly simplified form, that it's morally sufficient to get good control over auxiliary bilinear sums and so these might look like sum over integers n of size n with some coefficients alpha n, integers m of size x over n of some coefficients beta m, subject to the condition that nm is in your set A. And ideally, you'd like to show that this set is almost as if this was just a random condition. So if it was completely random, you might expect it to be holding with probability the size of A divided by x times so you'd like to show something like this, and these estimates all depend on some quantity capital N, and because we're having to do this in a hard analysis sense, we like to do this for hopefully a wide variety of different sizes of capital N, but it would certainly be sufficient to do this for n between x to 1/3 and x to 1/2 in general. Assuming you can, your set A is reasonably nice in some other technical senses. And it's these bilinear estimates that tend to always be the hardest to prove and the most difficult thing to establish. So how might one go about trying to look at something like this? Well, if you're looking at prime values of polynomials, all the polynomials that I look at, as I said before, are closely related to norm forms of algebraic number fields. And this gives you a huge amount of extra structure because you can make use of factorization in the number field to reduce your bilinear terms, and you have this nice concrete group action by the ring of units, so you're always counting everything in compact sets. And so it turns out that lots of the estimates just then boil down to lattice point counting techniques. So the Friedlander-Iwaniec result is really using the fact that you're looking at the norm form on Zi with the condition that one of your coordinates is a square. So x squared plus y to the 4 is just the norm of x plus y squared I. The Heath-Brown result is very much using the fact that x cubed plus 2y cubed is the norm of x plus the cubed root 2 of y. So this is like an element in the ring of integers where the final coordinate of the cubed root of 4 is equal to 0. And similarly, my polynomials, where I have degree d in n variables, are going to look like norm forms of an algebraic number field where I've set a whole load of the coordinates to be equal to 0. And each of these have slightly different difficulties that come out of it. The Friedlander-Iwaniec result really gets lots of difficulty because of the non-homogeneity of the polynomial, and this causes lots of very big technical issues. The Heath-Brown example, sparsity really hurts you, that somehow there's this big barrier at 2/3, and so being able to say anything at 2/3 is very difficult. Whereas in my example, the fact that you're setting lots of these coordinates to be equal to 0 causes slightly different geometric complications, and it's these geometric problems which are the key part here. So look at polynomials which are the norm form xn omega n of an algebraic number field of degree d, where omega 1 omega d is a basis for the ring of integers OK. And in fact, or an order within that ideal, and typically I'll be interested in taking this to be some sort of power basis, but I've set the final few coordinates here to be equal to 0, so I'm getting a sparse polynomial rather than having all the coordinates, in which case it's a trivial consequence of algebraic number fields that we can count primes, because that's just counting degree 1 prime ideals. So in this case, I'm really counting degree 1 prime ideals with this coordinate restriction that several of the variables are set to be equal to 0. And when I want to estimate bilinear sums like this, the standard argument is a judicious application of the Cauchy-Schwarz inequality. So you would typically try and bound this sort of sum here by applying Cauchy-Schwarz in the m variable, swapping the order of summation, and you'd then have something like m1 and m2, both of size x over n, where you have the conditions that m1 n is in A and m2 n is also in your set A. Now, when we're looking at things in an algebraic number field, we'd be summing over ideals in a number field, but we can more or less assume, let's assume that we've got class number 1 and things, so these are really vectors with respect to this basis, and we can say everything, all these vectors lie in a nice compact region because we can take a fundamental domain for the action of the ring of units. Morally, each of these two conditions is just imposing k linear constraints on the variable n in terms of the variable m1 or in terms of the variable m2. So generically, this is just counting vectors in d-dimensional space where we have n minus d constraints linear constraints come from m1 and n minus d linear constraints come from m2. And so this is lattice points in a bounded region. You'd expect typically that all of these linear constraints should be linearly independent of one another, and so the value of the inner sum here should just be the volume of the fundamental of the compact region divided by the determinant of the lattice. So this just reduces to counting lattice points on average in compact regions. So typically we know how to do this. However, there's some various obvious ways that this can go wrong, that these linear constraints could coincide, and so suddenly you have a higher dimensional lattice region to count in. But these linear constraints only coincide when these points align on some bad algebraic subvariety. Similarly, however, the determinant of the lattice could blow up and become very small as you approach one of these bad subvarieties. And so there are significant problems when M1 or M2 lie in or close to a bad subvariety, where close can be in a p-adic sense or in an Archimedean sense, in which case this inner sum here is suddenly much harder to count. Also, the idea that this counters the volume of the compact region divided by the lattice determinant is only actually true if the lattice isn't too skewed, and there's certainly going to be some vectors M1 and M2 where the lattice could be exceptionally skewed, and so the count will be wrong. So this is going to give you the volume of some region over the determinant of the lattice if you're away from bad subvarieties, and not skewed. And so, as I mentioned, to really get this sort of argument to work, the key difficulties then become quantitative, but slightly easy quantitative algebraic geometry, where you have to bound the number of points that lie on a bad subvariety or lie close to a bad subvariety in any of these two different senses, and show that there can't be too many pairs M1 and M2 that give you highly skewed lattices. But if you just believe me that you can do all of this, then you can estimate this region, you can get an estimate for this inner sum here, and then it turns out you can use the precise structure of these coefficients, beta M1 and beta M2, they're related to prime factorizations of M1 and M2, and use the prime number theorem for Hecke-Grossen characters to finish off and understand these bilinear sums. So then use prime number theorem once you've dealt with all these bad subvarieties and skewed lattices and things like that. But the key point here is that, yeah, I guess we have these very natural bilinear sums that come out. This reduces down to lattice point counting problems. The lattices are quite rigid, and you can get a pretty explicit description on what bad points can be whenever you have a very skewed lattice. You can't get a very good explicit description of when these points just lie close to a bad subvariety, but by using some ideas from quantitative algebraic geometry, you can say that there shouldn't be too many of these, and provided the sizes of all your elements match up in a reasonable way, you can show that they're suitably few, that this doesn't cause too many problems in the bilinear sums. One slightly technical issue, I guess, is that actually z equals zeros play a significant role, and so you have to take into account z equals zeros throughout the whole argument. But I don't really want to talk about that at all. So that's a brief idea of some of the ideas that go into the work on polynomials. Actually, the details are slightly more complicated, but if you want to look at primes with restricted digits, then the arguments still rely on bilinear sums, but they're slightly different in their nature. So here, the key property that you want to use is that you can Fourier expand this, the indicator function of your set A, I guess equals some sum over H of Fourier coefficients of your set A times e to the h n over x for values h less than or equal to x. And the Fourier coefficients of your set of numbers with restricted digits actually has a very concrete structure to it. And morally, you should think of this Fourier transform of numbers with restricted digits as being exceptionally small unless the point you're evaluating it at has long strings of zeros, consecutive zeros, or long strings of consecutive nines in its decimal expansion. So this is another way of repackaging the sort of digital information that's encoded in your set A. And most of the time, we expect this Fourier transform to be very small. And so then the nature of the argument depends very much on Diophantine properties of your set A. That you similarly expect the bilinear sums over this exponential factor to be very small unless your integer h over x, your fraction h over x, can be well approximated by a rational small denominator. So morally what's going on is that you have some question as to when can I have some fraction h over x which simultaneously is closely approximated by a rational small denominator and at the same time has very long strings of consecutive zeros or very long strings of consecutive nines in its decimal expansion. But I need to do this all in a fairly annoyingly quantitative sense. But if you just think about that problem on its own, there's one natural conjecture to have, which is whenever you're close to a rational small denominator, when that denominator itself is a small power of 10, then you're clearly going to get long strings of zeros in the decimal expansion. And this should maybe be the only case, since it's the only easy one to come up with. So one way of interpreting the argument is an application of the Hartley-Littlewood circle method, where we're using a different argument depending on the different Diophantine and digital properties of these Fourier coefficients. So for so-called major arcs, which is when h over x is approximately equal to over q with q very small, then this just boils down to counting our different elements in arithmetic progressions. And this is a fairly standard argument. We can count primes in arithmetic progressions. We can estimate bilinear sums in small arithmetic progressions quite easily. And it's not too difficult to count the number of elements, number of integers with restricted digits in arithmetic progressions. So boils down to counting in arithmetic progressions. Then there's generic h's. So this should be thought of if I just pick an h at random, how big should I expect the corresponding bilinear sums to be, and should these randomly chosen h's matter at all? And for these generic h's, what we'd really like to do is to get distributional estimates for the Fourier transform of numbers with restricted digits and distributional estimates for this Fourier transform which is related to the primes of these bilinear exponential sum estimates. So one distributional as functions of h. So unfortunately, this is essentially like getting distributional information of exponential sums over primes. This is a big, well-open, known question, and we can get moderate estimates, but essentially the best we can do in this context is just to use the Parseval bound, and we have very little information. So here we can just get L squared Parseval bound that shows that you do have square root cancellation in an L squared average. But we'd really like to do better than that, and it turns out that you can do much better than that for this Fourier transform of numbers with restricted digits, because it has a very explicit description. And so for this function, you can get essentially sharp LQ estimates for any given q greater than 0. So how do we do this? Well, it turns out you can you can approximate this very accurately, where the absolute value of the Fourier transform evaluated at some point h corresponds to the probability of a random walk, where the random walk, the path you take, is precisely tracing out the digits of h. So you're doing a random walk on the digits 0 up to 9. This has a Markov structure, so you've got finite transition probabilities, and then up to a good approximation, the size of your Fourier transform at h is precisely the probability that you took the path which is tracing out all the digits of h. And so this means that to get, say, an LQ estimate, you just need to understand LQ moments of the probabilities at overall paths, and you can understand this by just looking at the spectral information given by the finite transition matrix of this Markov approximation. So Markov random walk on the digits 0 up to 9 to the power n. So let's call this x, and then the probability that x takes the values h1 up to hj is approximately equal to the Fourier transform of our set A evaluated at the point that has digits h1 up to hj. And since this is just a finite Markov process, we can understand everything by some totally explicit transition matrix. And so the spectral information based on this random walk will give you complete distributional information for precisely how large this Fourier transform is. And then one slightly remarkable feature that's actually crucial in the first pioneering work of Maury Riva, and certainly in the work of Bourgain as well, is that this Fourier transform is actually remarkably small and has better than square root cancellation. So it has structural properties that mean it's smaller than you might naively expect. And this means that most of the time, in an L squared sense, this exponential sum has about square root cancellation. The vast majority of the time, in an LQ sense, where I can choose Q to be whatever I like, this is even better than square root cancellation. So it can only be exceptionally infrequently that this double sum here and the corresponding bilinear sums can possibly both be large, because I need both of these to be simultaneously large. So that means that for all of these values h outside of some small exceptional set, I don't need to worry about the corresponding bilinear sums. However, we know that there are certainly some h's which do make a large contribution, because we know these major arc h's do, although that's a very, very thin set indeed. And then the last thing we have to say is, well, what if there's some leftover set? Which is, again, morally this is morally saying that if you're just looking at h over x close to a rational small denominator, then because the digits repeat on q, it's quite easy to say whether there's long strings of zeros and nines. This only happens when you've got a rational which is a small denominator, when that denominator is a small power of 10. This is saying that we only care about things in a quantitative sense, and if I just pick generic fractions h over x, it's very unlikely that they're both going to be well approximated by a rational small denominator and have long strings of zeros and nines. And so for the vast majority of them, they're not going to contribute. But there could be some conspiracy that somehow there's some very large number of h's where they're all approximated by a rational with moderately small denominator and all have a bizarrely long string of zeros and consecutive nines. And so we need to rule out some possible exceptional cases. And here we need to reinterpret these bilinear sums in a much more rigid way. So the idea is that you want to pass from the bilinear sum being large to some combinatorial geometry arithmetic geometry, and we want to turn this into rigid algebraic conditions. And then once we have rigid algebraic conditions, these will be suitably explicit that we can handle them, and we can show that actually if you satisfy these rigid algebraic conditions, the bilinear sums must have been small in the first place. So that's a vague strategy of what I'd like to do. When you apply judicious use of the Cauchy-Schwarz inequality, for each pair, H1 and H2, you get a corresponding exponential sum, and H1 and H2 causes problems. If you have something like a double sum n1, n2 size, n sum over m of u of m, n1 over h1 minus, let's say n1 h1 minus n2 h2 over x is large. But by using geometry of numbers, you can say that this is only large if there's some high structural properties linking h1 over x and h2 over x. So there exists a cuboid in R cubed containing so this is a cuboid depending on h1 and h2 containing unusually many lattice points. So another way of saying this is for every pair h1 and h2, I can write down some very explicit cuboid in R cubed. If this cuboid contains roughly the right number of lattice points, so you should guess that it should contain roughly the number of points of integer coordinates should be roughly the volume of the cuboid, then it turns out that you can handle all the corresponding bilinear sums. However, if this cuboid contains way too many lattice points, then this is the only situation when things can turn bad. But if a cuboid in R cubed contains many more lattice points than its volume, then it has to be highly skewed in some way. So you can think that if it lined up with, say, the z equals 0 plane, then it could be very thin around the z equals 0 plane, so have a very small volume, but contain all the points in the z equals 0 plane, and this would be a cuboid of small volume but containing lots of lattice points, similar if it lined up along a line. And geometry of numbers shows that these are essentially the only two possibilities. That this only happens if the cuboid contains some line or lattice of low arithmetic height which is contributing far too many points. And if the cuboid contains a line or lattice that has too many points, this means that the pair H1, H2 actually has to lie on either a line or a lattice of low arithmetic height. So the point H1, H2 lies on the projection of a low height lattice or line. So if they lie on the projection of a low height line, it turns out that both of these points have a simultaneous rational approximation. So you've then got some nice algebraic structural information about this pair of points. If this simultaneous rational approximation has a small denominator, then we're essentially in the major arc case that we've already dealt with. If it doesn't have a small denominator, then I can redo all of these generic estimates for doing random walks and Markov chains within the fact that I'm only looking at things with denominators q. And by rerunning this whole argument, I can then deal with them because I've won from the restriction that they have a simultaneous rational approximation. And so that deals with the case when they're both on a low height line. However, they could both be on a low height lattice. But in this case, you have a very rigid algebraic equation for what they must look like. You must have A1, H1 plus A2, H2 plus A3, X plus A4 equals 0 for some small integers A1, A2, A3, A4. And you can just count the number of solutions to this equation because you know that although you know nothing about what set H1 and H2 lie in, you know that they have to lie in just some very small exceptional sets. And purely based on the fact that the set that H1 and H2 both lie in is this very small exceptional set, because we knew that generically we can handle everything fine, you can show that there has to be very few possible pairs of solutions to this. One way of saying this is that you could just loop over all possible choices of A1, A2, A3, and A4, and once I've chosen H1, H2 is fixed. And there's only a small number of choices of H1, but this is essentially square-rooted the number of possibilities of the number of pairs. And so just based on the fact that they're lying in a very sparse set, you can have very few solutions to this algebraic equation, and this means that there's very few possible pairs H1 and H2 which cause problems, and so they have a negligible effect on the overall bilinear sums. So I'm more or less out of time, but that's all I wanted to say about restricted digits. So I think I'll stop there. Thanks a lot for listening.
Okay. Okay. Well, so in any case, thank you very much for a nice talk. I have just a little remark about examples. There's also the Piatowski-Shapiro sequence as regards some example. Maybe it's on purpose you didn't mention it, or you had,
No. So that's another good example, I guess. Yeah, I just forgot to mention it.
Are there other questions or remarks? Yeah.
What if you looked at
It works.
no 7, they're just extensions?
Sorry.
What if you shifted the numbers with no 7 in their decimal expansion? Could you still get primes in there? So such a number plus 1.
Yeah, sure.
So that would work.
For every digit position, you're allowed to exclude a digit of your choice, which is almost the same.
I'm not quite sure this is exactly the question you were raising, or the answer. What you were raising is you take the numbers which have no 7, you add a 1, and you ask about primes in this sequence.
Yeah.
Is it what you answered to?
So,
yeah. Okay.
Yeah.
Good. Didn't get the point, but are there some other? Yeah, Olivier. Just 1 second. I bring you the tools.
Thank you. Yes, about prime values of homogeneous polynomial. If I understand well, if you assume that n is larger than 3/4 of d, you have asymptotic?
Yep.
Okay. And in the other case, then, for the upper bound, you can ensure that the upper bound is less than twice what you expect? Strictly less than twice?
Yeah, so, yeah, I think you get a very good upper bound. That you're having non-trivial type 2 information, so yeah, you're really getting a good upper bound here. I think.
It's really is 2 minus epsilon times what you expect.
Okay, I would need to check, but I'm pretty sure I get 2 minus epsilon times what you'd expect.
Okay, thank you.
Yeah, there are other questions, remarks? Okay, if not, then thanks again.